Within our lifetime, everyone in this room is going to be affected by CRISPR technology. CRISPR-Cas9 is a gene editing tool that has already begun to revolutionize modern medicine. Before I get into technology, I wanted to give a brief refresher on genetics. Every cell in our body contains DNA, which acts like a set of instructions or blueprints. These instructions are made up of a series of many genes that tell the cell how to make important substances, such as proteins. For example, antibodies are proteins created by the body that specialize in defending against pathogens. Think of DNA as a really long book, with each letter representing a piece of genetic information. The arrangement of the letters form words for what it codes for, such as hemoglobin or dopamine. It's super hard to pick those words out of a jumble, so to make it easier, special hints are placed around important sections of DNA that will need to be copied to make the protein. In this metaphor, the hint may look something like a ton of W's before and after the word hemoglobin, or a ton of X's before and after the word dopamine. However, sometimes viruses sneak into our cells and hijack our DNA to make harmful substances rather than the proteins we need. That's where CRISPR-Cas9 comes in. Some bacteria have developed an enzyme called Cas9, which works as their defense system against foreign invaders. When bacteria get infected with a virus, the virus injects its own DNA into the bacterial DNA. The bacteria using Cas9 marks this DNA with a special sequence. For example, alternating P's and Q's before and after the word bad viral DNA. The Cas9 enzyme recognizes the PQ sequence and knows to cut up and destroy anything in between. We found a way to use the bacteria's mechanism to benefit us. It's like a pair of molecular scissors that allow us to snip DNA at precise locations. This can cut out unhealthy genes that tell us to make mutated biochemicals. Even better, we've used the technology to allow those molecular scissors to bring along a healthy gene to insert. That's right. We can edit out bad genes that don't work correctly and replace them with healthy genes that make healthy proteins. It's easy to see why this technology has the potential to radically change medicine. Now, CRISPR technology has already had successful real-world applications. It's edited the genomes of mice to change the color of their fur, and it's reversed blindness caused by mutations. It's also slowed down the rate of rotting in tomatoes. However, it's had more significant applications in medicine. CRISPR was recently used to treat sickle cell disease. Sickle cell disease is an inherited blood disorder that's caused by a mutation in the genes that affects roughly 100,000 people in the US. The mutation in the hemoglobin genes causes the blood cells to make hemoglobin incorrectly, causing the blood cells to have a sickle shape. The sickle shape then decreases their oxygen carrying capacity and their ability to flow through blood vessels. This causes great pain to people who have this disease. CRISPR technology allows for some of the precursors to blood cells, also referred to as stem cells, to be removed from the patient's bone marrow. The mutation in these stem cells is removed and edited to make healthy hemoglobin. The rest of the person's unhealthy cells are wiped out using chemotherapy, and the genetically edited cells are then transfused back into the patient. These cells attach and multiply in the bone marrow, producing circular blood cells with increased oxygen carrying capacity and preventing sickling. The FDA approved this technology for mainstream use in December of last year. Nearly a dozen children and adults have already used this therapy, and over 60 hospital sites have been approved to perform it. The number of lives changed with this technology is expected to skyrocket within the next decade. This is just one of the many conditions CRISPR technology stands to treat and even cure. CRISPR technology has the ability to radically change medicine. It can cure life-threatening diseases and improve an individual's quality of life. However, diseases aren't the only large-scale issue we face in medicine today. Acute and chronic organ failure affects medicine on the national level. And as my classmate previously explained, there is a large gap between the available organs and the list of patients in need of transplants. In March of this year, Harvard Medical School physician-scientists transplanted a genetically edited pig kidney into a human. The patient had end-stage kidney failure and had previously received an organ transplant 5 years prior from a human, but it had failed. So, in alignment with the Compassionate Care Act, he agreed to accept an edited pig kidney transplant. The kidney had a total of 69 genomic edits, which included removing specific pig genes, which could cause an immune reaction, adding specific human genes to make it more compatible with the human body, and inactivating viruses present in all pig genomes to limit the risk of infection. And as my classmate shared in more detail, the technology has a very promising future. The number of potential applications CRISPR-Cas9 might have on medicine are nearly endless. Many diseases are not currently curable, and the treatments we offer for them only slow down their progression or treat their effects. And one such example is cancer. Cancer is a whole class of diseases in which some of the body's cells grow uncontrollably and eventually spread to other parts of the body. And as I said earlier, DNA is a set of instructions that are used when certain proteins need to be made. Mutations in those genes can result in a change of protein function, which can result in turning healthy cells into cancerous ones. Many of the genes that result from these mutations are called oncogenes. CRISPR-Cas9 offers several feasible solutions to treating cancer. One possibility is to inactivate oncogenes that are known to drive tumor growth. This could slow or even stop the progression of tumors. In a recent study, removing the MYC oncogene from animals presenting with lymphoma has shown to reduce tumor growth and even stop it in some cases. There have been equally promising studies showing CRISPR-Cas9 can be used to repair mutations that cause cancer in human cells as well, giving everyone a great deal of hope that a cure to cancer might be on the horizon. I have discussed many current and prospective applications of CRISPR-Cas9. Inevitably, each and everyone's life will be impacted by this technology as it continues to advance. There is no doubt that by utilizing CRISPR technology, we are actively reshaping modern medicine.